Hello, everyone. It is an honor to present our recent work, Pro, which has been accepted to CVPR 2023. First, we take a look at the snapshot of our work. Mean ensemble, i.e. averaging predictions from multiple models, is a commonly used technique in machine learning that improves the performance of each individual model. We formalize it as feature alignment for ensemble in open-set face recognition and generalize it into Bayesian ensemble averaging, BEA, through the lens of probabilistic modeling. This generalization brings up two practical benefits that existing methods could not provide. 1. The uncertainty of a face image can be evaluated and further decomposed into aleatoric uncertainty and epistemic uncertainty, the latter of which can be used as a measure for out-of-distribution detection of faceness. 2. A BEA statistic provably reflects the aleatoric uncertainty of a face image, acting as a measure for face image quality to improve recognition performance. To inherit the uncertainty estimation capability from BEA without the loss of inference efficiency, we propose BEA-KD, a student model to distill knowledge from BEA. BEA-KD mimics the overall behavior of ensemble members and consistently outperforms SOTA knowledge distillation methods on various challenging benchmarks. For the rest of the presentation, we dive into the details. The optimization framework of interest in this paper is to minimize the expected KL divergence between the prior and the posterior. We note that the prior can be Bayesian ensemble prior that involves the meta-information as an ensemble of aligned teacher networks. To align these teachers, we proposed algorithm 2 that first trains the first teacher and utilizes its resulting classifier matrix W to train the rest of the teachers. Our key observation in this method is that the randomness in the seed for training leads to the randomness in the learnable parameters /thetas. Therefore these teachers' parameters are identically independently distributed following some implicit conditional distribution. This further implies the teachers' embeddings are it following P, Z, X. Our next step then is to estimate the Bayesian ensemble prior using these samples and to parameterize the inference model Q, Z, given X. Now we show that by using Bayes' rule, the prior can be analytically determined in a form of RVMF distribution, where the distributional parameters are determined as the weighted mean and the weighted sum. We use another RVMF to parameterize the posterior Q. Then intuitively, Bayesian ensemble averaging returns a single averaged prior RVMF that accounts for the expected positions and confidence by all the ensemble members. To emulate the ensemble's probabilistic behavior, we employ a parameterized distribution Q to approximate the Bayesian ensemble prior. To push Q to P, we minimize the KL divergence between them. Our key observation here is that as the prior can be totally predetermined, we propose to minimize this surrogate loss in place of the original one. Our proposed model enjoys several theoretical benefits. First, we show that the differential entropy of our VMF density is a monotonically decreasing function of K. Then we utilize this property to further show that our predicted K can reflect the aleatoric uncertainty of a face image. Following SCF when we compare a pair of face images using the mutual likelihood score and use K to do the feature pooling when we have more than one face images. We conduct experiments on LFW, CFPFP, CPLFW, IJB benchmarks. Other implementation details are the same as in SCF. Experiments suggests that our proposed method is superior to all the other baselines. So in summary, we have presented Bayesian ensemble averaging, BEA, as a generalization of mean ensemble through the lens of probabilistic modeling. The proposed BEA can capture aleatoric uncertainty and epistemic uncertainty theoretically and empirically. We have also proposed BEA-KD, a single smaller, hence efficient, model that inherits the power of uncertainty estimation from BEA yet reduces the high computational cost of BEA inference. Consequently, BEA-KD outperforms SOTA-KD methods through extensive experiments. We believe BEA-KD could serve as a strong baseline and inspire further advances in OpenSet-KD research,